So last class I gave you some problems to work on. I hope you were able to get the answers to it. Are there any doubts or any questions regarding that? So let me see what are the problems. So I hope you had the time to go through it. So please do solve it. Okay. And if there are any questions, I can take it up, or else we'll move to today's class. Okay. So today's lecture will be on the concluding part of the time domain RLC response, which is basically the complete response. So if you recall our discussion on the first order systems, RLRC systems, we did the same thing. First we did what is called as the natural response or the transient response, right? So we went through all the exponentials, the way how it behaves and so on. And then later we said that if there is a forcing function, right? So then what happens? Okay. So same thing here. Till now we have looked at the RLC circuit, and we saw that if before time t equal to 0, if there was some initial voltage current conditions, and suddenly if that is removed, what will be the transient response, or what will be the natural response to the whole system is what we saw, right? So in today's lecture, we will see what happens if there is a forcing function to it, okay? Or in other words, if there is a step function which happens at the thing. So the solution step is very simple. So we know, how this systems work. So the solution to complete response basically is like this. First you determine your initial conditions, right? Okay, and then you determine the forced function or the forced response. Basically, what is forced response at t equal to infinity? What is the value? Correct. And then what you do is write the appropriate natural response. Why do we say appropriate natural response? The system can either be underdamped or it can be critically damped, or it can be overdamped, right? So you need to figure out which of the three categories it belongs to, and then write those appropriate expressions. And then what you do is you add the forced response to it, right? Because right from the beginning we have been telling that the total complete response is nothing but the forced response plus the natural response, right? Or for that matter, currents also. Okay, so you add the two, and then finally you evaluate the constants. Okay, now for evaluating the constants, you use initial conditions, and you also use derivatives. Correct. So this is the way we are going to do it. So let's take one example and let's try to solve it. Okay. So let's say there is a current source. This is the first problem. 4u of t. There is a inductor 3 Henry. There is a resistor 30 ohm. Okay. And this is defined as the resistor's voltage, and this is defined as the inductor's voltage. This is the inductor current. This is the resistor's current. Okay, and this is 1 by 27 farads, and obviously this is VC, this is IC, and you have a 5 ampere constant current source. Okay, so now the first part is, let's say, find all voltages and currents at t equal to 0 minus, t equal to 0 plus, and t equal to infinity. So shall we do that? So what is VL of 0 minus VC of 0 minus VR of 0 minus? Let's also find out IL of 0 minus IL of IC of 0 minus and IR of 0 minus. So first, can you tell me all the initial conditions?
VL of 0 minus should be 0 and VC of
Yeah.
0 minus should be 30 into 5, that is 150 volts.
Okay. Right.
The third one, what is it written? V.
VR.
Minus 150.
Correct. Minus 150 volt. So all of you, please work it out and don't try to think that you can do it later. So as far as possible, work it out along with the class. So that will give you the necessary speed as well as you can keep cross-checking answers.
The IR of 0 minus is minus 5.
Minus 5.
IC is 0 and IL
IC
is
is
5.
0. This is 5. Correct.
Sir, IC is 0. AC is written.
Oh, sorry. Yeah. I got
Yes.
So how about the voltages?
So IR of 0 plus is minus 1 amps.
Minus?
So IR of 0 plus.
This is how much?
IR. So IR.
Minus? Oh, I'm sorry.
So current.
Minus?
Yes.
Okay. How much is it?
1
Minus?
amps. So minus 1 amps.
Yes, sir.
Okay. Here, minus 1 amp. Okay.
And so IL is 5.
Yeah.
IL of 0 plus.
0 plus.
VC of
Okay.
0 plus also 150.
No, which one? What is
VC,
150?
VC.
VC
VC
is
of 0 plus.
150. Yeah. One is 150.
IC of 0 plus
And
is
so IS
4 amp.
4 amps.
4 amp. Okay.
VR is minus 30.
Right. So what is VL of 0 plus?
So result 120.
Yeah, it's 120. Okay, good. So let's figure out what is its value at infinity, the forced response. Let's say VL of infinity, VC of infinity, VR of infinity.
So IR is -1.
IR is -1. Okay.
IC is 0.
Sorry. IR is what?
So -1.
5. Yeah. IC is 0, right?
Sir, shouldn't it be -1?
Shouldn't it be minus?
Sorry, sir, -5.
Yeah. Yeah, this 5 amp current source has nowhere to go. It has to go through the resistor. Yeah. And IL?
Is 4, so 9.
9 amps.
Correct. 9 amperes. Okay. And so VL of infinity obviously will be 0, right? And VR of infinity is like it has 5 ohms, so it is minus 150, right? And this is plus 150 volt, right? Okay. All right. So now that we've got the initial and the final condition, so there is one of the reasons is that it is critical to find out how is the initial response. Okay. So you can see here that the inductor voltages and the capacitor currents can instantaneously change, and so that is important to identify. Okay. So now let's figure out. So what type of a circuit is this? Is this a parallel RLC or a series RLC?
RLC.
This is a series RLC. Okay. So is this a underdamped, overdamped, critically damped system? What type of a system is this? So we can do that by finding out. How do we find out what is the state of the system? You need to first find out what is alpha, and alpha for a series RLC is given by R divided by 2L, and omega naught of course is 1 by root LC. So by looking at these two values, we can find out whether it is an overdamped or an underdamped system. Correct? So what's our alpha and what's our omega naught?
Alpha is 5.
Yeah, this is 5 second inverse. This one is
So can you show the circuit
3.
again?
yeah,
It's 3.
yeah, that is 3. So alpha is 5 second inverse and omega naught is 3 radian per second, right? So is this an overdamped, underdamped, critically damped? How damped is it? This is an overdamped. Okay. So alpha greater than omega naught, so it is an overdamped system. Correct? Okay. Now if it's an overdamped system, then what is S1 and S2? Basically given by minus alpha plus or minus root of alpha squared minus omega naught squared, right? So both the roots of this characteristic equation will be basically real or imaginary?
Real.
It will be real, right? So S1 is S2 is
-1 and -9.
exactly. S1 is -9 second inverse. This is -9, -1 and -9. Okay. So now if for example, now of course you can write you can find out any parameter here, any voltage or any current or in this particular circuit. For just to solve one of the things, let's take the capacitor voltage. Okay, so Vc of t can be written as the forced response plus the natural response, right? Now, what is the forced response? Which is nothing but Vc of infinity, right? And what is our natural response? Natural response we have already known. We can say that this is a1 e to the power of minus t plus a2 e to the power of minus 9t, correct? For an overdamped system, basically our solution is a1 e power minus s1t plus a2 e power minus s2t, right? So our complete response will be the forced response plus the natural response. Okay, so anyway, because we have this complete expression, automatically our constants a1 and a2 will appropriately change. Okay, so now what is Vc of infinity? Found out that Vc of infinity is 150 volt. Okay, so the equation becomes 150 plus a1 e to the power of minus t plus a2 e to the power of minus 9t. Okay, so now what is our job? We have got the equation, right? We only need to figure out what is a1 and a2. So we already know how to do that, right? So we apply the initial condition. So at t equal to, let's say 0 plus, so Vc of 0 plus is equal to what? 150 plus a1 plus a2. What is Vc of 0 plus?
150. 150.
150, correct? So which means a1 plus a2 is 0. So this is one equation. Okay, so now let's take the derivative. First, let's dVc of t by dt at t equal to 0 is given by what? If you derive 150, take a derivative of 150, it becomes 0 plus minus a1 e power minus t plus minus 9 a2 e power minus 9t evaluated at t equal to 0. So this becomes minus a1 minus 9 times a2, correct? Now we need to figure out what is dVc of t by dt, right? So what can we say? So C dVc by dt is nothing but Ic of t, correct? So dVc of t by dt at evaluated at t equal to 0 plus is nothing but Ic of 0 plus divided by C. What is this value?
108.
It is 108, correct? So our equation now becomes minus a1 minus 9a2 becomes equal to 108. So solve these two equations and we will be able to determine what is a1 and a2.
So plus minus 13.5.
Plus minus
13.5.
13.5, yeah. So a1 is 13.5, a2 is minus 13.5. So Vc of t can be written as 150 plus 13.5 e to the power of minus t minus 13.5 e to the power of minus 90. So this is our complete solution. Okay, all right. And we can also find out the settling time. So settling time, so how do you find out settling time? So typically if it is 1% settling, what do? So you find out what is within 1% of the final value, correct? So basically your Vc of t should be equal to 0.99 times of Vc of infinity, correct? So for this, let's say VC of TS, settling time. So from this you evaluate what is TS. Okay. So that's how you do settling time. Okay. All right. So is it clear? So the procedure is pretty much same. Only thing is you identify what are the different parameters. Okay. So let me give you one more problem. This is IS. You have 20 ohm. This is VR, and you have 1 millihenry. This is IL. Okay, and you have a capacitor which is 10 microfarad. This is PC. Okay. Now the question here is, so find a IL of 0 minus, VC of 0 plus, VR of 0 plus, IL of infinity, IL of 0.1 millisecond. Okay. So and IS is given by 10 U of minus T minus 20 U of T ampere. Okay. So basically, before for T less than 0, it is 10 ampere, and T greater than 0, the current becomes minus 20 ampere. Okay. All right. So this is something, take it as a homework or an assignment. So practice these problems, because it's only when you work out problems that you gain the confidence and the experience to solve these things. Okay. So let me give you one more problem for you to work out at home, and that is, let's say this is VS. This is 15.625 Henry inductor. This is 50 ohm, 1 millifarad. This is VC. Vs is given by 10 plus 20 U of T volt. So you need to find what is IL of 0, VC of 0, and IL forced. Okay, IL of 0.1 seconds. Okay. So this one will be series or parallel RLC.
Parallel RLC.
This will be a parallel RLC. Okay. So always you have to make sure that you figure out whether it is an underdamped system or an overdamped system, and appropriately, use the right equations. Okay. All right. So please do. Yeah.
How is it parallel RLC? I didn't understand.
So you can see that it is, RC is definitely in parallel, right?
Yes.
And so here it's only the voltage source which is there. So the forced response. Okay. So what happens? So this is a voltage source, right? So the forced response, this is just going to be at 30 volt, and the voltage. So basically, the way in which it is going to operate is in the sense of a parallel. See, all resistor, inductor, and capacitor are connected to the same node. Okay.
Yes.
At this node. Okay. So that's the way that you figure out that it is a parallel RLC. Here, of course, it is that they form one loop in this previous problem. Right? They don't
So
share
like
a
we
common
can,
node.
so we can say we have to short out the voltage source and we can just open the
You can-
current source and
you
see
can
whether they
think
are
of
series
it.
or parallel.
Yeah, you can think of it that way. Yes.
Sir, doubt.
Yeah.
Can you please go to the previous slide?
Yeah.
Previous one. The settling time.
Oh, the settling time one. Yeah.
Yes, sir. So you said that 1% settling means the 1% of the maximum value of the VC of T. No? So maximum value will not be VC infinite. I'm calculating it is coming
Okay.
at 0.2746 times. So
Okay. Got it. Yeah. Okay. So yeah. So I should have clarified it. So when you don't have a forced response, okay. So there it is. So when we that settling time was in the context of and natural response only. There was no forcing function. That is like you energize the circuit and then you just remove all sources of energy. So the circuit is going to die down, right? So it eventually everything will basically go down to zero. Okay. And so in that context, when we talk about settling time, we talk about 1% of the maximum value. Okay. So let me explain. Thanks for bringing up this point. I didn't explain it. So that is like let's say you have a response. This is no forcing function. Okay. So all voltages and currents go to 0. Okay. So here let's say it is some underdamped response or something, it will go something like this. Okay. So this will be your, let's say if this is some voltage, this is your Vmax, and you take 1% of Vmax here, right? 0.01 times Vm, and this is how you find out the settling time, correct? But in the case of a force, so this is when you don't have any forcing functions. Okay. But when in the presence of forcing functions, now what happens is, so let me take a very common example of, let's say you give a step. Okay, let me take this example where you give a step. Okay, this is 0 to, let's say, 1. There is some R, L and C. Okay, so now what will happen? Basically, your if you're looking at, let's say, the voltage across the capacitor or something like this, okay, and so what will happen? So if it is an overdamped system, it will basically go slowly like this and it will settle. Okay. So if it is a critically damped system, it will be a little faster and it will settle. Okay. Now it is if it's an underdamped system, what will happen? It will basically go like this, depending on the alpha value. Okay. Probably this section is looking pretty bad. So, but let's see. Okay. So, but all of them will finally settle down to 1 volt here. All right. Okay. So, therefore, I mean, the forcing function will make sure, that is what we define as forcing function, right? Like at the end of the day, it forces it to go to a certain value, which is I of infinity or V of infinity. Okay. Now, when we talk about settling time in this context, we talk about how much time does it take for this function to go and come within 1% of the final value. Okay, that is to say, how long will it take to reach 0.99 times V final, okay, or I final. Okay, so that is how we define settling time. Is it clear? So the question is, for example, so this is a common problem that you would have you simulated this in LT-Spice in your ECAD lab? Step response of some RLC circuits.
So we have simulated some forcing response, but not using the step function or something.
Okay, so let me give that as an assignment. So please take a let's say this is inductor and capacitor. Take the same thing, put a step here, okay, and then you can put a step of 0 to A at time t equal to 0. So let's take 1 kilo ohm. This is 1 Henry, and or let's just say this is 10 microhenry and this is 10 microfarad. Okay, all right. So take 1 kilo ohm and change this value. Okay, so take R1 such that it is overdamped. Okay, R2 such that it is critically damped, and R3 and R4 both that they are underdamped. Okay, and in R4 basically you need to have should be less than R3. Okay, so two cases of underdamped where one is more underdamped than the other. Okay, and now you see how is your VC of T. Okay, and you will see that just by changing this resistor value, right, you will see certain changes. Okay, so I mean you will see all these different parameters. Okay, so when you talk about, let's say you have a system, you give a sudden jerk to a system. Okay, this can be a mechanical system, electrical system. Okay, so for example it can be, you know, some suspension system of an automobile. It can also be that, you know, you suddenly, you know, you have this digital signals coming in and you have some analog circuit where you suddenly, you know, turn on the power to an analog circuit, or you give a digital signal, you know, a 1-0 signal to a analog circuit, or a routing network, and how does it behave? How long does it take to settle? Okay, so all these questions are answered by these analysis. Okay, so the settling time in the case of a forced response is how long does it take for the final value to reach, I mean for the, you know, voltage or capacitor to reach within 1% of the final value. Okay, and the previous definition was valid only for only a natural response where there is no forcing function. Is it clear? Okay,
Sir.
yeah. All right. Okay. So now let's move to a slightly different discussion. Okay. Let's consider these two RLC circuits. So we have kind of come to the end of, you know,
of this course.
just hold on. Okay. Now what do you think will happen if, for example, our in our series RLC, the resistor goes down to 0, or for our parallel RLC, the resistance becomes infinite. That is, you have only an LC network. What do you think will happen?
Sir, it will go into underdamped mode.
So, okay, under
Operation
damped,
system.
It will be like a tank circuit, sir.
it will basically become a tank circuit. So this is the origin of tank circuit. So if you take an LC, so typically what happens is in oscillators, okay. So if you want to build an oscillator, so okay, let's start with this. Let's start with this LC circuit. Okay, as I mentioned, probably so many lectures back when we talked about, you know, inductors and capacitors. I mentioned that the loss if you take a real inductor, that is, you buy an inductor from an electronic component shop, okay, or you manufacture your own inductor or a capacitor, so it will always have certain element of loss. Okay, so we know that an ideal inductor is lossless and an ideal capacitor is lossless, right? Does not dissipate any energy. They can only store energy. So the effective loss of the circuit, of this tank circuit, right, of an LC tank circuit, is denoted by this R. Okay, many times when you build an oscillator, you may not even put a deliberate R there, because, you know, the resistance basically comes from the parasitic, you know, components in the inductor and capacitor. So it can be captured as a shunt R. Or in the same way, if you have a parallel RLC circuit, right, this R can very well represent the loss in the network. So if you eliminate, in this case, if R tends to infinity, and here if R goes 0, okay, you have a lossless LC tank circuit. Okay, so all of you are familiar with LC tanks, right? So how the energy transfer happens between the inductor and the capacitor. So have you already come across that in your school or
Yes,
maybe your
sir.
first year, right? Okay. So if you've already come across, then I think it should be, then I'll not go through it. So even when you talk about an underdamped response, okay, so when you have, if you take, for example, this underdamped response that I have drawn, okay, you will basically see the energy transfer happening between the inductor and capacitor. All right. Only thing is the envelope will go down. Okay. So if your capacitor voltage is going up, it means that there is energy being stored in the capacitor and the energy is getting dissipated, right? So so when the energy is being stored in the capacitor in this region, right? So at the same time, basically who is giving the energy? The inductor is giving its energy. Okay. So the inductor current will be basically going down, right? And then when the capacitor voltage, then what happens? It flips the sign. And then after this point, the inductor starts charging up. Okay. So let me maybe use a different color and try to draw it. Okay. So I can say that, if the inductor voltage is 0, maybe the capacitor voltage is 0, probably the inductor current also might start. So basically what happens is, let's say from this point, right? So the inductor is basically giving out energy, right? And then the inductor is charging up and the capacitor is losing its energy. Here inductor would have charged up, right? And then vice versa. Okay. So all these things you can basically plot it in the something like this. Okay. So this will basically be your inductor current and this will be your capacitor voltage. Okay. So you can see these things in LT Spice. It's easy to probe those nodes. Okay, look at the currents, look at the voltages. Okay, so basically the energy transfer keeps happening between the inductor and the capacitor. And what is causing this kind of an exponential decay is this element R. Right? So this resistor, these are the energy dissipating elements. Right? Now, in the absence of R, what will happen? If you just excite this LC circuit, what you will basically get is you will basically get sustained oscillations, right? You will basically have sustained oscillations. The amplitude will remain the same, okay? There will not be that e power minus alpha t will not be there because alpha goes to 0. Here, if you see, alpha is given by 1 by 2 RC. If R goes to infinity, alpha is 0. Here, the alpha is R by 2L. So alpha goes to 0. Okay. So if you don't have alpha, basically all you will have is, if you write the expression, is e power minus alpha t, some a cos omega naught omega dt plus b sine omega dt, right? So this is the expression. So this term is eliminated. You will only have sustained oscillations. All right. So the concept of an oscillator circuit, which we will see in analog electronics, is basically to somehow compensate for this loss in the LC circuit. Okay, if you can somehow provide energy to this LC tank circuit such that it compensates for the resistive dissipation, okay, the energy dissipation, the resistor here, you end up with an oscillator, and that is basically the concept. Okay, all right. So now let me also take you through the concepts of so I now it is like we have kind of come out of the time domain thing, and we will look at what is called as the let's kind of try to tie in both the frequency domain and the time domain aspects. Okay, so if you just take a series RLC, of course we can do it with the parallel RLC as well. Okay, and this is some voltage source Vs, this is Is. Okay, now what is Is? Let's just I here, V and I. So I of S can be written as what? V of S divided by the impedance, right? R, L and C. Now, because these are, frequency dependent components, you can write them as what? R plus SL plus 1 by SC. So have you studied this in Dr. Sudarshan's portion?
Yes.
Yeah,
Yes, sir.
right. So you can basically write it like this. Now, can you simplify this and see what happens? So SC times V of S becomes basically SRC plus S squared LC plus 1. Okay, right. So you can basically also write it as V of S. I want S squared to have a coefficient of 1. So what will happen? I'm going to divide both numerator and denominator by LC. So this becomes S by L, right? And then we have S squared plus, what do you have here? S times R by L plus 1 by LC. Okay. Now we can kind of identify some of the terms. So what can you say here? It becomes S squared plus 2 times alpha times S
plus omega naught
plus
square.
omega naught squared. Okay. Now what are the roots of this equation? So basically, if you take I of S or the I of S by V of S, the equation becomes, what is the root of this equation? It is minus 2 alpha plus or minus 4 alpha squared minus omega naught squared, right? Minus 2a divided by 2. So it becomes minus alpha plus or minus root of
Alpha square minus omega naught square by 4.
All right. So this is what you basically get. All right. And so what happens basically is, like you can see that you end up with a very similar form, right? You end up with a very similar form, and you can okay. So this is V squared minus 4AC, 4 omega naught. So it is, so omega naught squared only. Okay.
Yes.
Now, yeah. So what is this? This is nothing but your S1 and S2 that you found in your circuit, right? In your time domain analysis. So we approached it from differential equations, and we ended up with the characteristic roots to be equal to something like this. And here we did it in the frequency domain aspect, and we found that the roots of the system are basically like this. Okay. So this alpha is the damping factor, and then of course you have your damped oscillations. So if you want to plot in the S plane, okay, for an underdamped system, where will your poles lie?
Left side of
The thing. You'll basically have two real poles, right? Overdamped system, real poles in the left hand side of the S plane, right? For critically damped, how will your system look, or how will your poles look?
A single pole at
Will it be single pole?
sorry,
So it's minus alpha plus or minus root of alpha squared minus omega naught squared. Okay.
alpha
Right.
equal
So
to
alpha becomes equal to omega naught.
double pole.
So will you'll have basically two poles at S equal to minus alpha. Okay, you get it? So let me just say S1, S2, where it is overdamped. Okay, and for this, let me just put it as some S1, S2, critical damped, both poles are at the same location. So this happens, right? So S1 is equal to minus alpha, S2 is also minus alpha. Okay, so you have two poles at the same location. Now what happens if you have a critically underdamped system?
Two complex poles.
Correct. So you have complex conjugate poles. Okay, so it's not two arbitrary complex numbers, they become complex conjugate poles. Okay, so how will they look like? So basically they might be something like, this and this. Okay, let's say S1 and S2. So the real part is the same, the imaginary part, only the sign is different. Okay. Okay, and what can we say about the poles? So if they are closer to the origin, it basically means that it will have quicker settling, slower settling
Slow.
for the overdamped system and or the critical damped system. As these poles move this side, right, as alpha becomes larger and larger for all these three scenarios, right, as the poles move more and more towards infinity, then you will have faster settling. Okay, so here you have faster settling. Okay, at least for overdamped and critically damped systems. Okay, and even for the underdamped systems, of course, you make the thing. So if these poles appear closer to the y-axis, what happens is you will have very slow settling. Okay, for overdamped it will be slow, critically damped it will be slow. For underdamped also, what will happen? E power minus alpha t is very slow. Okay, so it is going to take a longer time to die out. Okay, and the limiting case is when alpha becomes 0, what will happen?
No,
Lie on the y-axis.
When alpha is 0, what will happen? The poles will lie on the
J omega
y-axis,
Sine circuit.
j omega axis. Okay. So the reason that I mentioned this to you is, okay, so many times you may not have an RLC circuit, okay, to talk about underdamped response, critically damped response, or overdamped response. Okay, you might get this kind of second order behavior even with your normal circuits where there are transistors, where there are only resistors and capacitors. Okay, it may not even need to be a electrical system, it can even be a mechanical system. But since you are all circuit engineers, right, we deal with electrical systems. Okay, you might have a transfer function where the components can be due to anything. Okay, it can even be some process plant that you are describing, it can be some circuit with transistors, or whatever it might be. If you have a second order system, okay, any second order system, it can either be overdamped or critically damped or underdamped. Okay, and that is done by looking at the pole locations. If you have two real poles which are separated from each other, which are not equal to each other, you have an overdamped system. Okay, and so you will not have any ringing, right? So this one has no ringing. Okay, both critically damped and overdamped system. This underdamped system will have ringing, and if the underdamped system's poles are closer to the y-axis, you will have more sustained ringing, and if they are farther away from the y-axis, you will have less ringing. Okay, you will have ringing, but it will quickly die down. Okay, is it making sense? Okay, and if your poles come to the y-axis, you will have sustained oscillations. Now what will happen if the poles move to the right hand side of the S-plane?
Unstable.
Unstable.
It will become unstable, because now alpha, if poles are in right hand side, alpha is greater than 0, which means it is exponentially increasing oscillations. Okay, so which is an unstable system. So this is the way that you will test the stability of systems. Okay, so just I want to make sure that you understand the relationship between the poles and zeros, which you find out in the S domain analysis. Okay, and the relationship between time domain. Okay, this is very critical. Many people, many students, and even engineers, professionals struggle with this. Okay, what is the location of the poles and zeros, and how does it behave in time domain? How does it behave in frequency domain? Okay, so that is what is. For example, I can relate it to the amplifier poles that we looked at yesterday, right? So if you take a BJT, common emitter amplifier, it has two poles, right? So what happens is one pole is much closer to the origin, which means lower bandwidth, and the other pole is at very high frequency, which means, which is farther away from the y-axis, which means it is at a very high frequency. Okay, so which means it is an overdamped system. It is not going to ring. But if you do something to bring both the poles closer to each other, they will start giving issues like, beyond a point, they will break out into complex conjugate poles. Okay, and then you will start having ringing and things like that. Okay, all right. So this I'll conclude today's class, and I think so. Have you guys studied resonance in your? Okay, I know I'm exceeding the time. I just want to know what all you have covered. So
Yes,
this
sir, we
chapter,
did some
yeah.
things, sir, in school.
Okay, the sinusoidal steady state analysis you have done, right? Like phasors and
Yes, sir.
nodal analysis, mesh analysis with complex impedances. So that you have done.
Yes, sir. Yes, sir.
Okay,
First semester.
first semester. And this AC power circuit power analysis, that is average power, concept of RMS, power factor, all that has been covered in first semester.
Yes,
Yes,
sir. They
sir.
have been.
Instantaneous RMS average. Okay, that is good. Polyphase circuits, this Y delta connections, Y delta
Yes, sir.
conversion. So that is also three-phase systems, three-wire
Three
systems.
phase. Yes, sir. Yes, sir.
Okay, right. And magnetically coupled systems, that is mutual inductance, transformer,
Transformer. Yes, sir.
Yes, sir.
that has been done. Okay, fine. All right. So Laplace transform and circuit analysis in S domain.
So going on, sir.
Is going on in Sudarshan sir's class. Okay. Frequency response of parallel RLC circuits. I will start. Okay. So that is chapter 16 in our network analysis, this Haight book, and then maybe I will go into two-port networks. Okay. All right. So next class I will start with the frequency response of parallel. I think resonance. Have you come across the concept of Q, quality
Yes,
factor?
sir. Q factor.
Okay. So which means I can kind of speed through that as well. Okay. So Q and other things, you did it in first semester or was it in school?
Sir, in school, and now Anup sir is also taking
Oh, okay. Fine.
with
Good.
respect to filters.
Filters. Okay. All right. Okay then. So I think we are kind of then maybe I will take two-port networks and I'll just see what I can do through this resonance and other things. Maybe one class I'll take and then I'll move to two-port networks. Okay. Okay. Thanks everyone. Have a nice day.
So for today's
Yeah.
lab, do we have, like you said earlier, we have
Yeah.
instrumentation.
So both are okay. Just a minute. So Bharat, what's the deal?
Sir, actually, fourth one man is not taking. So, like, if you're free, can we have it by 12 o'clock if everyone is fine?
Yeah, I am free. I am free after this. So 12 o'clock, 12 to 12:45, we'll have an analog electronics class. Okay, I want to start off with MOSFETs, and yeah, and after that we'll have. I'll also give you the problem for today's experiment. Okay. So 12 o'clock we'll have analog electronics. Okay. So thanks everyone. Have a nice day.